Oh, sharing my screen. Ding. Okay. All right. So first of all, we have the old tradition, candy. Yeah, you get 2 classes, two doses of candy. Inside, you'll find a little business card from my dentist. He will. Not so much. That was one of the things we missed from lockdown, is my tradition of bringing candy to the review. That didn't work in the online version of the class.
Just email it to
Email it. Here's a here's a receipt. Here's a coupon for one Snickers mini. All right, your questions. It does say not cumulative in the sense of the problems that we solved before, but there's a little bit here. I mean, you can't just forget that CFGs and are the definition for context-free languages, and PDAs can recognize them. I'm not going to give you a PDA to do like we did on the last exam, but for true, false, or multiple choice kinds of questions, you have to be able to recall that part of it. That regular languages are a subset of context-free languages. And even further, that Turing recognizable is the superset around CFLs and regular languages. So there will definitely be you can count on one Turing machine question like the there will be a Turing machine question like the little quiz or last homework I gave you, to look at it and figure out how would I move the tape back and forth in order to do this. So, but what's the point of that? It's getting you to recognize the right. I mean, in one sense, the limitations of what the Turing machine can do, but at the same time, recognizing that while it's limited in the way it represents stuff, it's still as powerful as a regular machine. So it can do that kind of stuff. So pseudocode, I'll try to, I'll make sure either I or the grader put in comments on, if you miss points on that. But the idea is present pseudocode that can have, you can put while or repeat kinds of structures in there describing. So your whole point, not so much, you're not making the state machine for the Turing machine, right? Well, all you're doing is describing, okay, first the tape is going to start here and move right until it hits this and mark it off and continue moving right to mark off the other one, whatever, and then back up to the beginning and keep going until it ends up with, you've used up all the all the ones on one side and there's leftovers on the other side. Did you have a question? Oh. Okay, I'll answer. I'll recognize your hand.
I have a question.
Yeah.
For that section, the Turing machine, would you? I know you said you have a problem on there, like the one we were just working on.
Yeah.
What about like in homework 3, where we had a state diagram and we had to, you were given an input, kind of
trace through
the entire state diagram of how that works.
Yeah, you should be able to do a simple one of those. Obviously not a drawn out one, but should be able to read and follow the notation on a state diagram. Not produce one, not create one, but given a simple one, be able to follow it. What else? Yeah.
Yeah, could we have an example which is just like onto a simple diagram?
Well, I guess if you wanted a example, what's the simplest one? I'm looking in the book on page like is this the one that does the like page 172? I'm thinking of simpler than that. I mean, like a well, that has 7 states, I guess. I would count the figure 3.8 as that has a little. I want to give you something that would probably not be quite that complex, just under the duress of taking the test, right? So, not trying to have no tricks or anything in there, but a simple Turing machine that you can tell what it would do. Just show, say, given a string, tell whether it would accept or reject this input, that kind of thing. So just following the notation, knowing the notation enough to be able to follow it.
Go back to chapter 2.
Mhm.
Did you say that we, on the exam, wouldn't have a problem like we had on the last test where we, given the CFG, is we have to use
You will not have that.
to build the EDA and
Right.
do the stack operations?
It sounds like fun, but no. You can't have one of those. Sorry.
Not asking about.
Oh, I thought you were requesting one of those. I could give you an extra credit one. No, just kidding. Yeah, so you don't have to worry about that one.
Maybe an example similar to a parse tree we would have to create on the test. It says,
Let's see, we've kind of done parse trees. I guess I would, rather than creating a parse tree, ask you what a parse tree is, or what it would show, or is this a valid parse tree for this string? Those kinds of things. So knowledge about, but not having to perform on that from chapter 2. This is going to be on paper. Oh, did I? Oh, that probably got left in from.
It just says draw it on canvas.
Not drawable in Canvas. Okay. Oh, I did say create a parse tree, but that's actually kind of left over from last exam. Yeah. Yeah. So this will not be in Canvas. I'll have to fix that. Yeah. 8.5 by 11. You can use both sides.
No, they're not open book. I mean, open up.
Did I say open book on here? Oh, I did say open book and notes. Open book and notes.
Okay.
I missed which class. But caution is that doesn't mean don't study, right? Because the having walked down the dark path of, oh, it's open book. I got this. Oh yeah, I know this. To have the shocking revelation that you ain't got it.
Will we be able to use our book if we have an electronic version?
Oh. Yeah. Yeah. Open book, I mean, it's kind of interesting from a teaching standpoint. Students like it, although it probably hurts them more if it coaxes them into not studying. But the time it takes to look stuff up is way longer. I mean, the test will be, we'll have a time limit on it, I'm aiming for an hour and 15-minute length. What that means is most people finish that in about 40 minutes at the most, majority. And I'll put probably an hour and a half time limit. Once I make it, I'll put a limit on it. But what that means is knowing the stuff is going to be the way more efficient and fast way to do it and comfortable way to do it than trying to look stuff up under stress and everything. It's not really good as a course in looking stuff up in the book. Yeah, thanks for waiting.
What time and day is the exam?
Should be Wednesday. I went and found this.
It's 12:40.
Oh, okay.
It's in the same.
Yeah. Okay. Yeah. So I'll post an announcement for that this evening for everybody to make sure. But yeah, so it will be here, but it'll be a slightly different, radically different time if you get right down to it. Yeah. I'll reiterate that in the announcement since I put it on the sheet here. Open book of notes.
And my electronic notes are good too then? My
Yeah.
notes are okay.
However, I will be monitoring and verifying that we are not doing a group exam. That's really that was one of the biggest hurdles, I think, for the online exam stuff was just to try and keep people honest in not making it a group effort. You can do it as a group effort. We'll just take the final grade and divide it by the number of people who were participating.
Go over the Turing thesis. I mean, I've seen as many different places you can find people talking about it.
Yeah.
Different ways of describing it.
There is. I guess to put it into the terms that we're trying to get across for our purposes, it's just that kind of the nature of computing as we know it. A Turing machine is as powerful as a machine can be, in short. So what that means is all of our current, even supercomputers, the concept of what it takes to solve an algorithm or to execute an algorithm is a Turing machine can do that. So it is as powerful as any machine in the sense of the class of problems that it can solve. Right, so not speed, we're not looking at performance, capacity, although the fact that it has an infinite tape does put it up there in the range of amount of, if you had the comparing your laptop to the specifications, how much memory does it have, and put it next to the Turing machine, and the Turing machine would definitely get the infinite compared to your 8 gigabyte main memory. Is that clear enough?
What we need to know about its proof.
No. So it is much like the P versus NP question, right? Which we said is still open, although there is no existing mathematical proof, final proof. This is also true of the Church-Turing thesis. From all appearances, Turing machine is as powerful as any other machine can be, and so it is largely accepted, but without a formal proof. And if you look in, if you try Googling and Wikipedia-ing stuff, you can get all kinds of speculations and opinions and stuff. What else you got? Yeah.
Later, will you be able to publish like similar questions like you did MP?
Oh, some sample questions? Let me see what I can do. The answer is maybe. Or my favorite, it all depends.
So this final is that on Wednesday, right?
Say it again?
It's on Wednesday?
Yes.
On the decidability chapter that we covered, in your review, it says know how the proofs are applied for decidable or not.
Okay.
Not recognizable or not decidable. Are you basically talking about the general approach used for the proofs to regular the contradiction?
Yeah. So I'm not going to have you reproduce the proof, but there are some conclusions. The nature of the proof is that it's a proof by contradiction, and it starts with an assumption that we could have a halting problem decider, right? So the contradiction comes when we find out that decider, if that decider existed, then we could feed a program that basically said it would stop. They could determine whether a program would stop or not, and it would give the opposite answer. So if a program would stop, it would analyze it and say, no, it won't stop. And if it would not stop, it would say that it would. And then you just feed it its own input, and it gives, we know that it would, basically it contradicts itself. When you feed it its own input, if it would stop, it gives the opposite answer. And so from that, we conclude that the halting subroutine that we needed to make that work could not exist. Let's see. It should be clear on right, a decidable problem will always stop with a yes or no. You're guaranteed that it will. A recognizable problem says that for strings that are in the language, it will eventually stop and recognize. It'll answer yes if you give it a string that is in the language. But if you give it a string that is not in the language, you don't know. It could keep running, or it may say, no, it's not in the language. But that may run forever is the halting, basically the essence of the halting problem, that you don't know whether it will ever stop. As far as producing, probably be able to describe it to him, to accept some language in a high level way. That's actually going to be in a problem that, given, here's the problem, right? This is exactly what the little sample, the last homework I gave you is doing that, describing what does it have to do? What's the pseudocode for how it has to move on the tape and fill in and mark stuff off. Okay, and then on the decidability chapter, just be able to recognize the these guys. These should be pretty intuitive from all the stuff that we did in the first chapter, right? All the finite automata we did, and the constructions and stuff we did. So you're not going to have to do any of those, but you should recognize that if you had a something that will, you can decide acceptance of a DFA by simulating it. You can do the same thing for an NFA by first, if you have the simulation for a DFA, you can apply it after you convert your NFA to a DFA and then use that same code. So kind of following the logic along that. You don't have to reproduce that equivalence of the DFAs. Basically the symmetric difference. You don't have to memorize that or anything. Is every CFL decidable? Yep, that's a decidable problem. Then let's see, complexity. All right, hopefully after the last lecture, we got some awe and shock and awe about the size of the numbers, the actual, how fast those intractable, right? So you should be able to identify what are the intractable functions that obviously you could do. You could modify them, but we looked at 3 different kind of major intractable functions of n, and those included what? N factorial, n to the n, and our friend the 2 to the n. So those 3 are in the intractable class. Obviously, any multiples or variations. N to the n to the n is a crazy fast-growing one as well. But we contrast those, right? Those would be exponential in nature, and we compare those to the polynomial kind. Polynomial ones are just powers, simple constant powers of n. And so those pretty much for our purposes are the discriminator between polynomial time type problems and, don't ever say non-polynomial, non-deterministic polynomial problems, which have exponential solutions and often incorporate the try every possibility kind of sort of, if you're looking for a touchstone on what might be an NP problem, something that you have to try every possibility tends to be either like a often that's a factorial that we looked at that with the password cracking idea of how many different combinations can you have, or even we looked at, didn't we take the 9 digits and show that would take you a really long time to try all the possibilities for that just on a 8-character password. So the whole heart of cryptography of having password protected access depends upon somebody else having an NP hard problem they have to solve, right? I mean, you want them to have to take decades to try all the possibilities on your password. And so the question of, are the classes NP and P equal? That means, is there really no distinction between what we're calling the hard problems, the intractable problems, and what that would mean that we just haven't gotten smart enough yet, or we haven't discovered a solution that will do that in fast time. If we were then, so the question of what's an NP complete problem? An NP complete problem is one which has been set aside, basically recognized as a problem for which, if you could solve this with a polynomial solution, then you could solve any other NP complete problem and essentially any NP problem using that same basis, because there are reductions. We talked about what a reduction is. We didn't really stress, but the idea is that all of them can be converted to each other NP complete problems. You can just apply a simple transformation, and get an equivalent. So if I can make one of those work, if I can find a solution to one of those, then I can make all of them use that same solution with just a polynomial time transformation. So a polynomial transformation plus polynomial solution is still a polynomial solution. Right? It takes a little longer, but it's still in the class of polynomial time. Let's see. Oh, did we ever get to the Hamiltonian path?
What?
I don't think we talked about Hamiltonian path last time. That's where it would have fallen. Okay, so the simple actually there's a typo in that. There's a simple path problem that your book designates as path, and that's, is there a path from one vertex to another vertex in a graph? And that's actually a polynomial solution. Hamiltonian path Hamiltonian path is P, polynomial, but the variant of that, the traveling salesman problem, is an NP complete problem. That's making a circuit. So the difference between finding just a path versus finding a circuit that returns you to the original spot, passing through each vertex once, is more difficult. There's not going to be a question about that. But why does anyone care whether P is equal to NP? There are lots of problems out there that would be solvable very quickly. Cryptography being one of the most relevant and at the moment. But any kind of matching, like we looked at the I guess the password, trying all the different combinations of the password. If you could solve it in polynomial time, then it would allow you to break security on just about anything. The key to that would be to make sure that you don't tell anybody that you found out how to crack every password, right? Because otherwise people would quickly figure out other more complicated ways to keep you out. Your questions. I think I'm out of stuff to add.
I guess specifically, is a non-deterministic Turing machine more powerful than a deterministic one?
That's a good one. What does our book tell us?
There's no.
Yeah, it doesn't change the type of problems that it can solve. Right. So, and we made a distinction that it's important. They should, if you haven't gotten that yet. There's decidable, which is, I know this will stop, and there's undecidable, which is, I can't tell whether this will ever terminate, so I don't know if it will give me an answer. Those are totally different because from P versus NP, so those are not the same question. We got undecidable over here, and we've got decidable, which is undecidable, don't know if it'll stop. Decidable, I know that it will stop. Now, in the decidables, we have the question of P versus NP. So we know they'll stop. It's just going to take a really long, we know for a fact it's going to take a really long time. So that's where the problem is in the P versus NP. So sometimes people get that, because we often end up talking about them in the same kind of time frame. NP does not have anything to do with undecidable. NP problems are decidable. They will stop. The problem is the complexity is that they'll take a really long time to stop. So it's not like we don't know whether it'll stop. We know it'll stop. We know it'll take a long time. Yeah, you can ignore that.
So you're saying that the P versus NP consideration is haven't even covered it completely with the realm of decidable?
Yes. Yep.
Okay.
Yep.
And, okay, but there's undecidable and even unrecognizable, but those,
Right, which we had left for,
okay.
I mean, or unrecognizable or yeah, recognizable can, we don't know if it'll stop. And then there's languages that are not recognizable that we didn't do anything with.
So what undecidable doesn't then automatically default to, and it's not even the same.
Correct.
Subject of discussion is what you're saying.
Correct. Yep. 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 So undecidable is can we even find a solution? And there's some languages that you just can't. You can't make something that will stop. And then in the world of decidable, we have P versus NP, and they're all decidable. Just we may not like the decision. We may not like how long it takes to make a decision. Let's see. I think the only like solvable problem is like the Turing machine one that is homework, the last homework. The rest could be matching. Maybe a few true false. Try to we have good true falses. Anything else? How many questions? I'm guessing, yeah, pretty much to be determined. I'm imagining 20-ish. So I do try to avoid high point problems in general. So you just personal experience. All right. Filled up with enough candy to get you out the door. Came in late. There's candy mixture. All right, I guess we'll see you a week from today. Note the, it's according to the final exam schedule. I will also send out an announcement to confirm it, but it is different from the time the class normally meets. So, and that's pretty universal on all your finals. So make sure you do a double check and that you're there when you're supposed to be there.
I wanted to see if you could clarify for me on the
Yeah.
homework. So you talked about how it doesn't matter how the string ends up. But
Right.
then-
All you care about is that the N has to end up where
Yeah.
on the
But
left
the
hand.
book talks about marks. Are you kind of meaning use the T or the N's as the marks, or that's where I got kind of confused?
Oh, in this, so the initial setup has like a pound sign on each end.
Yep.
And so that's what you can use to decide whether to, when to stop going forward and to start going back. But when you get all done, then just move to the left-hand mark and then write an Y or an N over top of that
Okay.
left-hand one.
Cool, that makes sense. Then. Thank you.
I know there's a lot of different ways to write
Mhm.
algorithms. And I ended up doing mine something like this, and
Okay.
then when I went into the test, I saw it said, well, I want you to number the steps, so I just kind of left it like that and
Yeah.
did numbering and sub-numbering of all the steps, so.
Yeah, the numbers are just for clarification to
Okay.
make sure it's kind of sequential and
Okay, I
readable
just-
for grading.
Yeah, I just
But-
wanted to make sure that was okay.
Yeah.
I mean, we mainly did it like this because then I also just whipped up a Python script just to, well, I just wanted to
Good.
see if,
Oh,
okay,
good.
well, what I'm doing is
Yeah,
is that implementable and,
right,
you know, I mean, I knew it was, but
sure.
just to see how it would work out.
Oh, that's good.
Okay, there's, you know, the book, every book seems to have a different way of doing their narrative description
Yes.
of how these things go.
Yeah.
Okay.
No, that should be perfect.